The title of this presentation is Effects of Perturbed Depth Sensors in Autonomous Ground Vehicles. The authors are Tony Pinar, Adam Webb, Jessica Brown, Tim Havens from Michigan Technological University, Brendan Alvey, Guy D'Souza, Derek Anderson from the University of Missouri, and Stanton Price from U.S. Army ERDC. The work described here was conducted at Michigan Technological University in Houghton, Michigan, and was supported by a contract from SOS-SEC managed by the U.S. Army Engineer and Development Center and by a grant from the Office of Naval Research. In this work, we investigated the effects of perturbed LiDAR measurements on an autonomous ground vehicle. And to do that, we came up with six kind of baseline perturbation models. And then we developed a behavior-based autonomy for the vehicle that had three different behaviors: obstacle avoidance, waypoint navigation, and path planning. And so finally what we do is we combine those together to demonstrate the autonomy functions in the presence of these perturbation models. All the results you see here are simulated. And to do that, we combine together AirSim and the Unreal Engine. And so AirSim is a package in which you can simulate autonomous vehicles, including drones and cars. And so in this work, we used a UAV, and the Unreal Engine then is the physics-based backbone of AirSim, and allows us to simulate the measurements from that autonomous vehicle. In this case, we're going to use LiDAR. And so the arena on the right is what we're going to use here. We kept it very simple. And so the experiment we're going to do is we're going to have a start position and an end position, which we call a goal for the autonomous vehicle. And the idea is that the autonomous vehicle needs to navigate from the start position to the goal, avoiding obstacles along the way. This is the outline of my presentation. I just gave you an introduction. Next, I'm going to talk about the perturbation models that we developed, then the autonomy algorithm, and then the experiment, and finally we're just going to summarize. The perturbation models that we came up with here are more fundamental models based on like noise and additions and alterations to the LiDAR point cloud. And so we implemented these with middleman ROS nodes. And so essentially what happens is that this middleman ROS node accepts the LiDAR measurements which are produced by AirSim and Unreal Engine, processes those LiDAR measurements to add the perturbation model to the point cloud, and then republishes the perturbed point cloud to be processed by the autonomy algorithm. This slide shows the first model, which we call SNOW. And so on the left, you can see the no perturbation point cloud that's produced. And that grid in the center is simply to note the location of the drone in this case. So you can see that there are obstacles to the left and the right and in front of the drone, and then also in the upper left and upper right corner. And those are those blocks that you saw in that arena that I showed previously. On the right shows the perturbed point cloud with what we call the SNOW measurements. And you can see why we call it SNOW here, because really what the perturbation is just randomly located points added to the point cloud. And those points move around as the vehicle moves through the arena. And so this kind of simulates like spurious sensor measurements that could be produced by a sensor in the real world. The second perturbation model is called noise, and this simply takes in the raw point cloud as published by AirSim and Unreal, and adds a additive white Gaussian noise to each of the points measured in that point cloud. So you can see on the left there that the points of those obstacles are a little bit more, say, fuzzy in that view. And then on the right we show the wall that's right in front of the drone at the top center with no perturbations added, and then also with the perturbations added on top of it. So you can see this just makes these measurements more noisy. So you can simulate various qualities of sensor measurements. The third model is just like that previous model that we discussed, except for the noise is now just happening in certain angle cells of the LiDAR. So we call this local noise. So you can see in the top center of that image on the left there that the middle of that wall that is detected by the LiDAR is more noisy. And so this kind of, you could simulate degraded quality of sensor measurements in specific scan angles in a LiDAR. The cloud's perturbation model is now a little different than the noise ones you just saw, in that it's adding points to the point cloud. And so you can see on the left is an image of the point cloud with no perturbation, and on the right is an animation where this cloud's perturbation has been added. And you can see the cloud that's to the front left of the grid there, and these points are produced by drawing from a Gaussian distribution that is centered in a location relative to where the drone is. The blob's perturbation model is like that cloud's perturbation model in that we're adding points to the point cloud. And so again, you can see this no perturbation point cloud on the left, and on the right is an animation that shows these blobs. And the way that these blobs are added to the measurements is by drawing a random distribution of spatially correlated points around the drone. So you can see that the blobs appear as like spurious measurements that have some spatial correlation to them, or they look like blobs. The final perturbation model that we're going to use here is called local blanking, or local blanks. And so again, on the left I show the no perturbation point cloud, and on the right I show the point cloud with this perturbation. And this simply simulates missing measurements in certain scan angles of the LiDAR. So you can see in that wall that is directly in front of the drone, or in the top center, there is now a missing section of that point cloud in the center. And so again, this can just simulate a malfunctioning LiDAR where you're missing some sensor measurements. So I just described the 6 perturbation models that we're going to use, and so next I'm going to describe our autonomy algorithm. The autonomy algorithm that we developed for this work is based on behaviors. And so there are 3 behaviors: obstacle avoidance, goal seeking, and avoid large turn. So as the robot is moving, at each time step it's going to determine its direction of travel based on those 3 behaviors. And those behaviors are aggregated in a cost function, which we describe next. At each time step of the simulation, the drone evaluates this cost function. And so you can see here that the variable in this cost function is theta, and where theta is the directions around the drone in 360 degrees. And so then at that time step, after evaluating this cost function, it's going to go in the direction of travel, or the theta that minimizes this cost function. So let's look at each element of this cost function. The first term is the obstacle avoidance term. And so you can see here, this is just simply an exponential term that's dependent on that function r theta. R theta is the distance to the nearest obstacle at each angle theta. So you can see that that term is going to be inversely proportional to that distance. So the closer an object is, the greater that term is, hence it's going to avoid obstacles. The second term is the goal-seeking term, and so this is simply just looking at the difference in the direction of travel and the direction in which the goal is, which is that theta star. And so that's minimized when the drone is pointed right at the goal. And finally, the limit big turns term is simply just a hard side function where for certain angles around the current direction of travel, which is theta t, it is 0. And so we're using a theta b, which is that limit of pi over 6. So it can make turns in either direction of within that pi over 6 angle of the current direction of travel. And then if you go outside that pi over 6, then that hard side function shoots up to a value of 100,000, which essentially just eliminates all solutions that are outside that range. So now that we have the perturbation models which affect those LiDAR measurements, and we have an autonomy algorithm that processes those measurements in order to move the drone from its current location to the goal while avoiding obstacles, now let's put those together in an experiment. The image that you see in this slide is the arena that we used for this experiment. So there are blocks that are used as obstacles for the drone, And what happens is the drone is placed in the start position, indicated by that blue circle and start position, and then the drone must autonomously navigate towards that goal position, which is indicated in green. And so you can see in order to do this, it needs to make its way around those obstacles that are in the arena. We evaluated the cost function at about a 4 Hertz update rate, which was driven by mostly the computational limitations with the simulation. We used 72 equally spaced angles around the drone to evaluate that cost function, and the drone was moved in the direction of travel that minimized that at 1 meter per second. So it moved at a constant velocity of 1 meter per second. When the robot reaches the goal, the simulation ends. And so we evaluate how well the autonomous drone moved through this experiment by the path length that it took. Obviously, we want the smallest path length possible. And thus, what we do is for each of these perturbation models, we run this experiment 10 times to see the overall effect of these perturbations. This shows the result of this experiment with that snow perturbation model. And so recall that the snow perturbation model simply adds in random spurious points into the point cloud. And so on the left you can see the path lengths that were taken with no perturbation present. So you can see that the drone moves forward until it hits that block and the obstacle avoidance kicks in, turns to the right, and then moves around that block, and then finally towards the goal. And so you can see each of the 10 paths were pretty much the same with no perturbation. With the snow perturbation, you can see that the 10 paths that the robot takes are quite different. And so you can see that it's trying to avoid those spurious measurements that are happening as it's moving around. And in some cases, you can see that it even has to back up away from the wall before navigating around it. This slide shows the drone paths taken with the blobs and the clouds perturbation models. And so recall that the blobs and clouds perturbation models add points to the point cloud, where the blobs is like spurious little blobs that appear around the drone, and then the clouds perturbation model is a cloud that appears in the view of the drone relative to that location of the drone. In this case, we placed that cloud, just like you saw in the animation previous, kind of to the front left of where the drone is pointing. So you can see in the blobs path lengths, it kind of looks very much like the snow path lengths in that it's moving around as those blobs appear in and out of its view, and in some cases even backtracking before it moves forward. The clouds perturbation model, you can see a significant difference in the path length after it navigates around the blocks. And this is because as it goes around that edge of the block and then can see the goal in the front, to the front left of the drone, that cloud is preventing it from moving in that direction. And so it isn't until it gets almost level with the goal that it can finally kind of move around that cloud and move towards the goal. These results show the path of the drone in the presence of the perturbations that add noise to the existing point cloud. So again, you can see on the left there's the no perturbation path. In the middle is the noise perturbation path, and you can see in this case that the drone essentially just gives a wider berth to the obstacle. And this is because the point cloud that presents itself to the drone around that obstacle, the noise essentially blurs the boundary of the obstacle, and hence the drone thinks that the obstacle is larger than it really is, and hence is just simply giving the obstacle a wider berth, not really excessively affecting the path. In the local noise example, the noise was added to around the middle of that block relative to the drone's path. And so you can see at first the drone gives that block a wider berth, but once it gets around the noisy part, which again is the middle of the block, this path more resembles that of the no perturbation case. This last result shows the effect of what we call the local blanks perturbation. Again, the no perturbation path is shown on the left. In this case, the local blanking effect was right in front of the drone, so kind of the center of the drone's viewpoint as it moves forward towards that block. And so what you can see happens is that the drone gets very, very close to the block. And this is because it really can't see that block until that block starts to appear in the left and right scan angles relative to where the drone is looking. So at that point, it starts just kind of bouncing off the block, not literally, but in the obstacle avoidance sense, and really gets close before it stops moving forward. And then as you can see, as it moves around the block, that local blanking effect no longer has an effect, and so the path more resembles that of the no perturbation case. This slide summarizes the results we just looked at. The table at the top, labeled Summary Table, shows the mean path length and the variance of the path length over those 10 runs for each of the perturbation models, starting at the left with the no perturbation, then the snow, the noise, blobs, clouds, local noise, and local blanks. And then the raw results from each run are shown in the second table, the results per run. So you can see from the summary table that the blobs had the most effect on the path length taken by the drone. And this is because the blobs really would appear spuriously as the drone was moving around and had that spatial extent as to perturb the path of the drone as it was moving. The perturbation models that had the least effect on the path length were the local noise and the local blanks models. And this was just simply because, you know, these perturbations only exist in a certain viewpoint, some angles that the drone is looking at from its LiDAR. And so once it gets around the block and that those local noise and local blanks no longer are in effect, then essentially it follows the no perturbation path. So in summary, what these results really give us is a kind of a fundamental look in the way that different perturbation models affect that autonomy behavior when it's using LiDAR as its sensor to move around obstacles and seek a goal. To summarize, we developed and executed an experiment to test the behavior of a simple autonomous algorithm on a drone using a LiDAR in the face of certain perturbations in that LiDAR measurement. And the drone was tasked with starting from a start position, moving around an obstacle, and going to a goal position. And we tested 6 different perturbation models. These results really provide a pleasing connection between the types of perturbations that it could be most disruptive to autonomy. And so now what we can look at is, you know, how do these perturbations occur in the real world, and how can we make autonomous algorithms more robust in the face of these types of perturbations or combinations of these perturbations. So thank you for listening. I appreciate it.